if you look on lecture number 2, we were understood, I thought right away to start originally special relativity, but then I found out that it's not right because you will miss a lot of things all the way, and better to complete our mathematical education to get mathematics closer to the language of physics. In order to reality, the classical physics generated calculus, and we got used to differential equations, and those were the language fitted very much to this description. While we go to modern physics, we have to get a little bit better mathematical description. Why I call it better? It contains the previous one, but it's doing it a little bit more accurate. And we're missing two things. One of them are tensors that we'll discuss today, and then is a shorter topic about for 15 minutes, 20 minutes, will be for the next time, is variational principles. The first topic is to describe different mathematical model of different physical quantities. You need tensors, and to get conservation laws, not by tricks, a systematic way, we need the variational principles. So we'll cover those two topics within a lecture and a half, and then we'll start special relativity. So we talk about lecture this, the topic is tensors as a mathematical language of physics. Okay, we start mathematical representation of physical quantities. Physical quantities can be direction independent or direction dependent. Direction independent quantities are called scalars, which are always presented by a number with physical units, meters, seconds, newtons, etc., as you've seen in the homework. Direction dependent quantities are vectors represented by arrays of numbers in a given basis. So the vector is really some physical quantity, it doesn't have coordinates, but in order to work with it, mathematics cannot work with some abstract object. You can work with numbers. So you pick up a basis. When you have a basis, you have an array of numbers. We'll need some kind of linear transformation between bases and linear transformation of spaces. Both of them are represented by matrices, which are already two index arrays, a different SO arrays, but with different indices. We'll have to talk about metrics, since we'll have to consider spaces which are not flat. For instance, consider the problem which was treated in science for thousands of years, how to use a map to define distance from the map to reality. So when you translate distances from map to reality, it's not only simply multiplying by a number, you have to consider at each point how to translate from the distance on the map to the distances in reality. So that's done by a metric, describing the distance between two close points, also represented by two indexed arrays, similar as matrices. But the mathematical dependence on the choice of basis differs from that of linear transformation. So we see that even things are arranged similarly, they behave differently by transformation from one basis to another. So they are different objects. We have to have a notation that takes care to distinguish between them. Good enough that from this notation you'll be able to come up to know all the answers. So in all those cases, tensors are arrays of numbers. It can be one number as in the top on a scalar, but it can be an array of numbers labeled by some index set. It can be two indexes, one index, and which both define the address or position in the array, as well as the dependence on the choice of basis. So the indexation has to be done in such a way that if you know what is the array in one basis, I have to be able to say how it looks in another basis. If I don't know, that means I didn't describe the physical object. I'm describing a physical object which is expressed only by array. So it can be expressed by different bases, and I have to be able to identify that both arrays describe me the same object. Now, this is very similar, this construction is from a different area in computers. How is the memory of a computer built up? And on a chip, you have cells, memory cells. Each memory cell contains information and numbers, some kind that you put in. And how you identify them, you look on its position. It is like the index. The index is defining you the row and the column on the chip. And when you give the row and the column of the chip, you can read the information which is there or write in. So it's very like in the tensors. You have values and addresses given by the position of in the array. We have even higher order ones, like if you have stress tensor, it's of higher order than 2. And in general, we have to be able to handle any number of indices. So that's brief description, and we'll go slowly, get it better understanding. One of the important operations there is some kind of generalization of the dot product. You know that we have two vectors in Rn. We can multiply their coordinates, add them together. That's the dot product. So we assume that in Rn, both are from the same space, and we have a way how to combine a number associated with them, or the scalar product. So I want to show you that this operation is also in very different situations also. For instance, you start with a vegetable store. You come in and you want to buy a few vegetables, peppers, tomatoes, cucumbers. And how we buy, we pick up and we put them on the weight, and we get a collection, an array, the weight of the peppers, the weight of the tomatoes, and the weight of the cucumbers. Then there is inside another array, which is called the price, P1, P2, P2, 3 of each one of the items. And the total cost is exactly a dot product. We take the two arrays. We have two arrays, W1, W2, W3, P1, P2, P3. And the total cost is multiplying them like a dot product, the element of the first array with the second one, the corresponding ones, and adding them together. This can be taught as you have to pick up a basis. E1 will be 1 kilogram of peppers. E2 will be 1 kilogram of tomatoes. E3 will be 1 kilogram of cucumbers. Then what are the W1? You're looking how many proportional from the basis. W1 you get 2 kilograms of cucumbers, is twice the basis E1, twice the basis E2, twice the basis E3. And then the prices are the prices per the basic vector. 1 kilogram of peppers, 1 kilogram of tomatoes, 1 kilogram of cucumbers. So first of all, we see that we have two arrays very different units, and still we can consider the total cost. Also, they behave differently if we will change the basis. For instance, we decided that we don't want to work in kilograms, we want to work in pounds. So we changed our basis. What will happen with the weights? The weights will get multiplied almost by 2, while the prices will get divided by 2. And the cost will remain a scalar, the same scalar. That means they behave totally different by change of the basis. And that's exactly what we will have to consider to understand. There are two types of arrays. And their behavior is they change the basis, then the changes are reversed in some sense. Let's go there in physics. We have also dot product, which is a scalar, a physical quantity, a number, physical unit, which is independent of the coordinate system. For instance, if we have consider motion, some force moves some object on some trajectory, we can calculate the mechanical work done for this motion. What it is the dot product of the force and the displacement vector. They are also not the same units, and how we get a scalar. If we change the units of the length, the force will change because the potential, the gradient will change, and the displacement will change, and they will change differently, but the dot product will be the same. And another example, the power is the dot product of the force and velocity vector. So it's also independent on the coordinate system. So we have a similar thing like in the example with the vegetable star, some kind of operations on pairs of arrays, which each one of the elements behaves differently, but the dot product is the same. Now let's look how this is in a general, in a vector space. Arrays in a vector space and its dual. It turns out that what we have seen are a connection between vectors and how they're called covectors. Covectors are elements of the dual to a vector space. A dual to a vector space is the space of linear functions. In Rn, the dual space is also Rn. So we got used to identify them. And therefore, we don't see the difference. But when we come to physics, everybody has to take care of the units. And we found out that they are different objects. Also, people that come from Banach space theories, they know that the dual space is not the same as the space. It is much larger. When you go to quantum, they became even extremely different. The space of states and the dual space is a big difference. But we'll mainly today discuss on the finite dimensional. So we'll be able to pick up what is a basis in a vector space, and the dual will call covectors. We pick up a basis Ej of vectors. We don't consider norms, etc. Need only linear dependent vectors, and we have dual covectors. In the dual space, which are called covectors, another basis. What is considered a dual basis is the following. Vk, that is this linear functional on Ej, gives you 0 if k differs from j, and 1 when they are equal. That means that the dual basis. Well-defined quantity, and such functions generate a basis on the dual space, and this will be the dual basis. Delta is the Kronecker delta, which is 1 when the indices are the same, and 0 otherwise. Then we can introduce for vectors coordinates. That will be how we got the arrays. It is done the following. The coordinates xj are such that your vector is a linear combination with those coordinates of the vector basis Ej. At this point, don't pay attention why sometimes I'm putting indexes up and down. It will be understood from the next slide. But that's the right way how to put them. For covectors, it will have also coordinates, and their coordinates for them, I'll put the indexes below. In this way, I'll know to distinguish them. If I see the index upper one, it is for the vector. If it is lower one, it is for the covector. And the same way, fk, dk. You see in those sums, there are always one index, and the upper one, and the other one is lower one, and they are the same. Okay, Einstein's summation convention. That's one of the big things that Einstein brought in his convention. Otherwise, all the papers looked a lot of sums, and in GR they had to have 3 or 4 sums, so it became almost impossible to see what the formula is. So he said, why do you need the sum? We'll make a convention. If you see in an expression the same index on the top and the bottom, that means you sum up by this index. Such operation is called contraction. So you had two arrays, and you generate from them a number. So instead of having arrays, now we have a number. Coordinate transformation of vectors. Now we want to understand how you move from one basis to another, how the coordinates change. That means we are considering the same object, but represented by two bases. Now we have to understand how we identify the two arrays represent the same physical quantity. And these are called the coordinate transformation. The coordinates are the arrays, how they are transformed by choice of the basis. So how we change the basis is done. Let's say we had a basis Ej, and we want to have a new basis. They usually denote them by Ej prime. Another set of indexes, Ej prime, has nothing to do with this J. J prime is another letter. Now what you do is the following. You look this vector Ej. It's a vector, and you can represent it in the new basis. So it has coefficients. The coefficients denote L with J upper index because we need sum by them. A vector is a sum of the coefficients times the basis vector. Now, in order to remember that it came from J, we have to keep his index below. There's very strong rule and tensors. If you write an identity, you have to check that all indexes are right on both sides. So we have here index J on the right, index J on the left, and J prime, since it has on the top and the up and below, it is a dummy index, it doesn't exist. So it's well written. So we have now such an array now, depending on two indices, J prime and J. This is called the basis transformation matrix. It tells you how I transform from one basis to another. Now how we transform vectors. A vector is, we have the same vector. That means xj prime ej has to be the same as xj ej. That means in the two bases, they have to represent the same physical quantity. So this equality must hold. I'm substituting here what's written here, and I'll get Lj prime j, ej prime. I can cancel ej prime, and I'll get that xj prime must be written Lj prime j, xj. It was written at the beginning on this side. The product is commutative, so we can move it back and forth. And look, when you look at such expression, this can be taught that what we learn matrix multiplication. When we arranging the two indices, we always keep one index for rows and one for the column. In order to get closer to the one that we use, this is the row, because we used to put them on the same level. The first one was the row, the other one was the column. So always the upper index will be the row, and the lower index is the column. That means they're always in this way and stable. If it would be the other way, it will fall apart. So the matrices are always the upper indexes close to the letter, and the lower index is a little bit removed from it. If I don't know how to write it, if they are in the same place, it means the same thing. It helps you to understand when you go to multiplication, the contraction has to be on the indexes which are close one to other. So in order that J will be close, this J from L and X close, so they have to be in this way. This means if you write it in a matrix, X has to be written from the right. Or multiplication will be of the vectors from the transformation matrix from the left. L is not linear, it's from the left. You'll see in a minute that there is also from the right. Now when you go the same thing on the dual basis. On the dual basis, we will denote the transformation. We have to, once more, on the dual basis, the basis is bk, and we want to express it in the new basis. And you get another array with two indices. See, it is a difference between the one here, the primed index was on the top, here the primed index is below. They are different. Now let's look, the definition of the duality of the basis was that if we'll apply Vk on Ej, we'll get delta Kj. Let's substitute it. Vk is this one, and Ej is written here. We substitute. Now we have Vk prime on Ej prime is also a dual basis. It's delta Jk. That means I have to make this one and this index the same. So it is Rk, J, L, J, J, and that's matrix multiplication. Matrix multiplication is also putting the two matrices and contracting them by the indexes which are in common in them, and the order of them is as they are written. The R has to come before L. The matrix multiplication is not commutative, and it's understood if you put it in the other way, it's a different object. So let's see. We started with the identity matrix, and we got as a product of two matrices. That means R as a matrix is the inverse of L, as we have seen earlier. So that's not example was, it's a general fact. The transformation of the coordinates of the arrays when you move from one basis to another. On the vectors, it acts by multiplication from left by some matrix, and it acts on the dual vectors, which we'll be able to get some constant by applying one to other. It acts by an inverse transformation and from right. So this will give you later you understand why matrices are transformed in this way, why metrics are transformed in different way. Everything is built up in this slide. Now, look what we got in, how we get transformation of vectors. Of covectors is by right multiplication by this matrix R, which is the inverse of the matrix L. So we know now how we have to transform coordinates from one basis to another basis. That means if we will keep our notation right, putting the indexes up and down, we'll know exactly how to write the transformation. That means we'll be able to identify the same physical objects even though it is presented by different arrays. Now we can define exactly what a tensor means. So we have to start with an index set, which is mostly the index, the basic set, the basis is numbered. And in physics, we have two types of numbering, 1 to n, or we start from 0 till n minus 1. In relativity, it's used the second one, where 0 is the time. So, but anyway, we have a basis of consisting n elements, and I is the index set we run from, and this set capital I. We have to have multiple indices, as we see for matrices, and we have a multi-index set I vector consisting of indexes I1, I2, IP, and with each ik is from this index set, and its cardinality len times k. And we have those transformation L. If we have for a multi-index, we simply take the product of them. And here's the definition. A vector, a tensor of rank PQ represents some physical quantity by an array of values T in upper index, bold I, and lower index J, labeled by the set of indexes bold I belongs to IP, where the P is the first number on the rank, and the second number is the number how much we have in lower indices, which transform with the change of the basis. When you go to a new basis, we multiply by L the upper indices and the lower indices by R. You remember that R is the L inverse. Here I didn't wrote right and left if you want to keep in the matrix notation, but the index of higher order, then it's hard to speak about the rules that we got used, even if it is possible. I remember when with Bernie we had the first big problem to solve how to identify we came to the JB star triples. We had to do a calculations. Efros had a hypothesis what kind of object I obtained with Jonathan Razi in our paper. And we had to test it on matrices of order 2 in power n. So it runs very fast that you can hard to do it. We asked somebody to do the calculation. He was a very good programmer. And he showed us how you can check all those complicated calculation hypotheses by using matrices of any dimension and any number of indices. He put all the possible matrices in a 3-dimensional array and have done multiplication with those arrays, and everything worked perfectly. And he showed us eventually that the hypothesis was wrong, and then it came up with the JB star triples. So it is possible to work with arrays with very high rank. And people in computers know how to work with it, because it's really built up very close to the ideas of computing. So I think if we'll be taught proper way, linear algebra will see, and a lot of things from calculus will become much better understood if you use the tensors. Operations that we have in the tensors. First of all, we have, if they have the same rank, same set of indices, you can add them and multiply by numbers. Simply the numbers that are there, adding and multiplication, not used too much, but if you have the same indices, you can add them also. There's a multiplication of two tensors. That means you multiply their values and put the index, the combined index. That means you add the indexes on the top, add the indexes on below, you get a big tensor, not used too much. What is used the mostly is this one, contraction of a tensor by a contracting index. It means contracting upper and lower indices. How you know which index is identified by labeling them by the same letter. You want to contract by some index, you have to label it with the same letter. Then you know you have a contraction. A contraction of a tensor of rank P and Q is a tensor, I call it contraction of T. It's of rank P minus 1, Q minus 1, because the contracting index got erased. So the rank went down both on the top and down. And what is the contracting? It involves omitting the contracting index and taking the sum of all values of the original tensor values with the same contracting index. Let's take an example. You have n equals 3 in order to not spend too much time. And we take a tensor of rank 1, 2. The top one has only one index, which is on the value 1, 2, 3. And the below has two indices, k and j. And I want to contract it. That means I want to contract this upper index with this lower index. I could do with the first one, doesn't matter. And call it bk, because we'll have no j, we'll have a covector. The answer will be a covector. How we obtain it? For each particular case, I have to take all a's at which the upper index is equal to the lower one. J is the same, so we have the 1, 2, and 3. We'll get A1 with the upper one, K1, A with upper 2, K2, and A3 below K3. Add them together, and that will be the contraction. It's very simple, very easy to write down a program to doing this. You have the same contraction. Okay. Now let's see how this can help us to understand a lot of things. Okay, let's start now a linear transformation. It means we have, for instance, we want to rotate all our space. Rotation is described by linear transformation. How we define a matrix of a linear transformation. So we have a linear transformation T mapping a vector space L into L. What we do, we check what it is doing on each basis vector T, J, write its coordinates in the same basis. Now, except the first example that we had, transformation matrix, from now on, we'll work with the same basis. We have only one basis on the space, and everything is done in the same basis. So therefore, in tensors, we never write the basis because assume the basis exists, and you write only the coordinates, and you know that the same answer you'll get if you go to another basis. So the connections will be the same. So you get some kind of universal formula. Okay, now let's check what the indexes are. If you apply it to EK, you'll get this is a vector. When you write to EK, it has to have an upper index. And the lower index comes because we started with the EJ, and EJ had a lower index, so you have to have also a lower index here. You'll get an array with two indices, upper and below, and we can think about it as a matrix. This is a tensor of rank. What is the rank? One upper and one lower is of rank 1, 1. So the matrices of linear transformation are not I and J are not the same. Therefore, when you transform the rows and you transform the columns, it's not the same. And remember, we had this L inverse, which is this for R, and it's multiplied from the other side. That gives you the right way why the transformation matrix is in this way. Because one of them is a lower index, the other one is an upper index. Now, okay, when you look what is doing of arbitrary number x, a vector x, arbitrary vector x is described by its coordinates, xj, ek. Then using t is linear, is this is a sum, but the sum can be done later. Xj could be taken out. Tj is exactly this expression. Substitute in, and you get here now such expression xj, akj. We can write it this way. Ek. That means t of a vector x is such thing. This thing is the same as take the multiple, the matrix of A by the vector x as a column. Now you remember xj is it corresponds to the matrices as the row, the columns, and okay. No, the rows or the column? Yeah, the column. We are summing. I will take the fixed row K and summing by the columns, one to other, and xj is really for xj it is the rows, the numbering, but it is multiplying this way. It is the same as taking this matrix multiplying by the vector. Means here it's really the matrix is multiplication of the vector x. How you get product of matrices? Very simple. You had a map from A to V, then from V to V, then another and the result B from V to V, and you look on the coordinates and you get the transformation of the coordinates. So on the coordinates, you get that the transformation is also a convolution, contraction of the vector B with the vector A, and the order has to be in this way, because we are applying into vectors, and A has to be multiplied first. Multiplication is done from left, and then the answer has to be multiplied by left by B. So it is the product of A and B is given by a matrix B times A, and it's simply a contraction by the two indices which are closer to each to other, those two, and you get another matrix. For instance, a very simple proof, the associativity of the matrices. Associativity is simply write down what you mean. AB is this one times a matrix C, so you have to define this index, contract with this one. And the other way, you contract those one with some index L, and then you have contract those one. So really, both sides is contracting A with two indices B and C, by J and L. So the difference between is them, the order that you sum up. Here you summed up first of all by J, and then you summed up by L. And here you summed up by L first, and then by J, but summed up the same number. So really, it is associativity of the addition implies associativity of the matrix multiplication when it's written in tensor notation. If we think about this as in the matrix form, it's totally not obvious. And here it became very simple consequence of the definition. The metric ds defines the distance between two infinitesimally close point x and x plus dx. That's exactly what I told. We want to have to measure the distance between two close points in some vector space V. In general, the formula is given, the distance has to be a scalar, and it has to depend on x and dx. And dx, it has to be some kind of quadratic, it turns out. And this is the formula. It has to be an array with two indices, I and j, and they both have to be lower indices because dx are the same as vectors. And in order that you'll get a number, g has to be with indices below. In Euclidean metric, g is the identity matrix, and then you'll get some dx1 squared the Pythagorean theorem. But in a curved space, you'll get some kind of coefficients. If you want to work on the globe, and then you have one of them, dx will be the radius of the earth times d theta. The other one will be cosine theta times d phi times the radius of the earth. It will be depend already on the point. And you'll get once more the Pythagorean theorem, since the two vectors are perpendicular locally, and you get a similar thing. So in general, that's the general metric is of this form. But the two indexes are low indexes, so Gij is a rank 0 to symmetric tensor. Now we have also a very important property, symmetry. Symmetry of tensors. We have done it in bound symmetric, we have the symmetric and anti-symmetric. But in tensors, you have to be careful what does mean symmetry. And not always, as we look at that, they look symmetric. Symmetry can be defined only when the indices are on the same level. You cannot talk for operators about being a symmetric operator. It is not, it is true only when you are working on Euclidean space. In Euclidean space, we are identifying the dual and the space itself. But if you are not in Euclidean space, symmetry has to be considered only for tensors which have symmetry of the indexes which are on the same level. Because it has to be the same by changing of the bases. And since the top indexes and the low indexes change differently, symmetric in one basis will not be symmetric in the other one if they are not treated in the same way. So why is this one can be assumed symmetric? We want to describe the metric in most compact way. Since in this sum, you get two terms, the xj, the xi for two indexes, and you get in the different order, but the product is the same. So you get everything will be the sum, gij, dxi, dxj, plus gji, dxj, dxi. So meaning is the physical meaning is only for the sum. So you can take them both equal, and it will give you the same ds. If they give the same ds, don't put extra non-physical assumptions. So we always assume that this tensor is symmetric. It means Gij is the same. That means the dimension of it will become small. Now we can define as a dual tensor is simply like if they would contracting the indexes there between them to getting the identity matrix. If you have a metric then you can perform raising or lowering the indices. And we'll need this thing sometimes. For instance, we want to have an operator which corresponds to a symmetric tensor. So you can define the symmetric tensor for something when the indices are low, both, and then you can raise it by the metric. And you will call this corresponds to a symmetric tensor. But that's how we will do it. So if you want to have a vector, and this vector we want to load in this, we take it a contracting with Gij. The J index went, and we get a covector. If we have a covector, by Gij up, we can raise the index. So we have a way, if there is a metric, to raise and lowering index. There are theories which are called pre-metric, which tries to do something without metric. Then you must keep each tensor which is placed, because you have no way to change the position from lower to up. Now we want to introduce another thing which is called the Levi-Civita symbol. The Levi-Civita symbol, very important symbol, it's a tensor, purely antisymmetric. We have seen the previous example as symmetric one. This is changing the indices don't affect the value. And here it's totally antisymmetric. Any two indices are changed, you get a change in sign. Of rank 0 n, all the indices are on the same level, totally antisymmetric. And here's the definition, very simple definition. It has n indices exactly as the dimension of the space. If two indices are the same, that means you didn't cover all the indices, it is 0. When it is not 0, when you add all the indices and you have a permutation of the natural order 1 to n, and if this permutation is even, it's 1, and it is odd, it is -1. This tensor has a lot of applications and very important. The first thing is it defines your determinant of a matrix in a very simple way. What is the determinant of a matrix? You write this matrix by the columns. The columns are the second index. So you write it explicitly 1 to n. And then what you do, you contract this ijk when you put the entries of the matrix corresponding to the same sequence. This is the definition of a determinant. Easy to prove it. What are the properties of a determinant? Changing two columns has to change the sign. Changing two columns change the same of epsilon to indices. Since it was purely antisymmetric, it changes the sign. It is linear, this definition, each one of the columns, obviously, from the definition. And what we'll do if we apply it to an identity matrix, the identity matrix will have only non-zero term when I is 1 and j is 2 and k is n, and it will give you 1. So this expression has the value 1 on the identity matrix, which is supposed to be antisymmetric and linear in each column. So it is the determinant. Let's check it for n equals 2. When epsilon is not 0, is only 2 of them, because you have to have only 1 and 2 and not repeat it. So you have 1, 2, 2, 1. And for 1, 2, you have to have A1 on the top. And in below, you have always here 1, 2. We have 1, 2. And here, for this one, we have 2 on the top and 1 on the top to be the same as this one. So this one is 1. So you get A1, 1, A2, 2. Minus, because this is an odd one permutation, and the product of diagonal elements minus the product of diagonal. It's worthwhile to do it once with that n equals 3 to see that it gives you the right formula of determinant. Very nice formula, how to teach determinant, much easier than you taught in a regular course of linear algebra. And here I'll prove you a very complicated theorem. Determinant of the product of two matrices is the product of determinant. really what you need is really to write what you want, and everything works. If C is the product of A and B, write the definition of determinant written here. Each one, C, you write in the components A or B. Combine all the terms with the indexes A. And here you're missing only that they are not organized in the same order. So reorganize them by using epsilon. And what you'll get is the determinant of A. Take it out and you'll get epsilon with the indexes B. Will give you the determinant of B. So such a complicated theorem follows really from the good definition. Tensors are very important. Using this Levi-Civita symbol is very important. Another product, the vector product. What is the vector product? You have two arrays of numbers, x and y, and you want to define a product antisymmetric. So probably you need to have Levi-Civita. Apply Levi-Civita to them, and you get not vector, it's a covector. We were used to have a vector, not the vector product is a covector. If you check what happens with the transformation, it transforms not as a vector. And you see later, like for electromagnetism, such expression occurs for the magnetic field. You have two vectors, the magnetic field, strength and the velocity, both are vector, and the acceleration is obtained is a covector, because it's the same as the force, which is a covector and not a vector. So things that we didn't pay attention without considering tensors now have to be paid attention, and they'll give us the exact things which are true and what is not true. If we get something because we didn't identify the right a vector equals to a covector, it's wrong. It has to be everything, the indices has to add up in the right way, and everything has to be within this notation. Right. Now I want to finish with vector analysis. Vector analysis is also done much better if you use tensors. So what is vector analysis? We're talking about functions and differentiations and arrays of functions. All the things will be now better defined if you use tensors. We start with Taylor series of a decomposition of a function. X is a multiple variable in Rn. We added delta x and we decompose it. We have a constant term, a linear in delta x, quadratic in delta x, etc. What we know that the linear term can be written in the following way. The gradient, df dx1, delta x1, df dx2, delta x2, etc. This is a dot product. Let's identify what are the two vectors. Delta x is a vector. The difference of two vectors is a vector. But what is the gradient of f? Let's check what is happening when we change the basis. When we change the basis, the f dx k prime is the chain rule, the f dx j, dxj dx k prime. This matrix has the index, primed index law. It is not L, it has to be written R. It's multiplication by right. It is a transformation of covectors. So the differentiation, the gradient of a function is not a vector, it's a covector. And therefore it's a covector, it has, applying it to delta x, which is a vector, gives you the linear part of the change of the function. Now we have an interesting notation introduced that used in this differentiation is used by the same index, but showing that it's not a component, they put a column before. So when you see f column k prime, it means it is the f dx k prime. Now the force is negative of the gradient of the potential, so force is a covector. And therefore, work was f dr. A covector can be multiplied by displacement, which is a vector. They are contracted. They give you a number, the work. So this gives the justification how we get the work is independent of the choice of basis, because F transforms as a covector, displacement as a vector from one basis, and application of one on the other is constant, is independent. Now, very important also, when we have a covector field, it's a field at each point you have a covector. This is also one form. What is one form? A physical quantity that exists for it, a line integral. Now, it's very important to understand when we talk about fields, vector fields, in mathematics, we thought we have line integrals, we can take surface integrals, we can take curl, we can take divergence. How? The same different things for the same object. Not in physics, there's no such thing. In physics, there's no vector field. Each vector field you can have only one type of integral. For a force, there's no meaning for taking a surface integral. No meaning to integrate a force. But integrate over a line is the word, has perfect meaning. Since the force was a covector field has line integrals. Why? Because what you want under the line integrals, you have to find the xk. The xk is an upper index. So in order to give a scalar, you have to have, the vector has to have a lower index. So only covectors are one form. Now, how we differentiate them? A one form can have only one derivative. And the derivative of a covector is curl. How it is defined? Here's the definition. How you can differentiate. You had a f was lower index. When you differentiate, you get another lower index. And you want to get a vector. How you get a vector? You will contract it with the Levi-Civita with upper index. And the curl will be a vector field. You differentiate a covector field, and the result is a vector field. So once more, we have to understand when we get gradient, we get always a covector. Covector is one form, and a derivative of one form is curl. You cannot define divergence. Divergence of this doesn't have any sense. So for any vector field, there's only one derivative, one type of integral. They are different vector fields. They are either covectors or vectors. Let's continue. If we have a vector field, then what, let's call it GR, it has upper indexes, vectors. What kind integral we can have? We cannot generate a one. If we'll take GI dr, we have two indexes on the top. How we'll get a scalar? No way. But you can get surface integrals. What does it mean? That those GR represents flows. For instance, you have flow of heat. You can consider a surface and how much heat went through the flow, through the surface. Now, how you'll get it? You'll have this vector D with upper index. On the surface, you have two coordinates, the U, dB, or both have the upper index, and then you contract it with the Levi-Civita, and you'll get a number. Now, what will be the derivative? Even much simpler. Derivative is contracting. You'll have J has an upper index. You differentiate, you get a lower index. You can contract it by this index. So you get the first coordinate will be differentiated by x, the second one by y, and the third by z. If you think for a while, strange derivative, why we had to differentiate g1 only by x, g2 by y, all of them depends on x, y, z. Why we get such a strange thing? But that's exactly the only derivative making sense by the definition, by using tensor notation. So the differentiation of a vector field gives you a scalar, difference as the curl gives us, a covector field gives us the vector field, but when you differentiate a vector field, you get a scalar. And if you do in the forms, you already see why it is. it is a 2 form. When differentiate, you get a 3 form, and 3 form is a density, and a density is a scalar. Now, I want to finish to give you what is the Laplacian. Everybody in physics knows that the Laplacian is second derivative. Strange combination. You take the second derivative by x twice, add the second derivative by y twice, second derivative by z. Why such a combination will be physical? And if you look, this is the diagram. We start with the potential. You know what, okay, let's do first of all, with the potential, you take the gradient, you get a field, F. The field, the force field. If you differentiate once more, you get 0. Because differentiation of forms, twice differentiation gives you 0. It's a good exercise to see. If you take the curl of something which is the gradient, is 0. Curl of gradient is 0. So you cannot go from here, from this F to G by differentiation. And I'll explain you how you go there. Then you have to get some kind of flow. To understand from F how to go to G is a different thing. You have to raise the index. We have to raise the index. And raising index depends, as we said, on the metric. And the metric mostly depends how you feel the environment, what it is. It will be once for charge, once for gravitational field, etc. And then you differentiate once more, and then you get a divergence of a gradient, and when you raise the index in between, you get the Laplacian. I can explain you intuitively very good on the case of heat equation. On heat equation, it goes, well, U is the potential, is the temperature at each point. When you get the gradient, you get the difference in temperature. That's F. Difference in temperature generates a flow of heat. The flow of heat is exactly opposite in the direction of the difference of the temperature and depends on the material. The raising of the index is always dependent on the surrounding. But it is a tensor which raises U lower index to an upper index. Then you have the flow of heat. When you differentiate, you find the source of the heat. And really, the Laplacian connects you the temperature caused by the source of the field. So here you'll have the sources of the field at the end, and then you'll be able to find what is the temperature. So that's the physics behind those analysis, the vector analysis. And very important to follow, understand where we are in a vector field, it's a covector field, etc. Okay.
Thank you. Thank you very much.
Thank you. Bye-bye.
Thank you, Jacob.
Very much.
Thanks a lot.
Thank you.
Thank you.
Bye-bye.
Bye-bye.
Bye. Thank you.